The rock can even be moved by a force that you can't see, if you do this, for instance. When you do that, the force moving the rock is called gravity. Gravity is a force pulling the rock toward the center of the earth. Gravity pulls everything else in the world toward the center of the earth also, including you. Gravity was pulling on the rock all along, of course, but when the table was there, that kept the rock from moving down. If you remove the table, you allow the force of gravity to move the rock. And when you pick the rock up again, you use another force, this time to lift it. So whenever you make this rock move, you do it by making a force act on it. In fact,
weight versus mass. If anybody ever asks you what a Newton is, yes, you could give them an apple, or a couple of golf balls for that matter, or a small flashlight battery, because all of these have a mass of about 100 grams. And when the Earth pulls them down with an acceleration of 10 meters per second, we say that the force of gravity acting on them is 1 Newton, or that the apple, the 2 golf balls, and the flashlight battery are all pulled down to Earth by a force of 1 Newton. How many newtons are pulling you down to Earth? Well, the simplest way to measure a force is to use a Newton spring scale. If we hang the apple on it, we see that the Earth is pulling the apple down with a force of 1 Newton. And if we hang you on the spring scale, we see that the Earth is pulling you down with a force of, let's see, just about 600 newtons. So now we know how much you weigh. What you weigh merely means what force of gravity is pulling you down to Earth. That's all weight is, the force of gravity. Remember how keen physicists are on Latin words? Well, gravity comes from gravitas, which is simply Latin for weight. But you thought you were weighed in kilograms, didn't you? That's true in everyday life, but not in physics, which has to be very careful about these things. In physics, kilograms measure your mass on a balance, but your weight is always measured in newtons on a spring scale. You'll have noticed by now that you can usually work out the number of newtons by multiplying the kilograms by 10. 100 grams, or 1/10 of a kilogram, is about the same as 1 newton, and 60 kilograms are about the same as 600 newtons. But if 1 kilogram is the equivalent of 10 newtons, why bother to make a distinction between a mass of 60 kilograms and a weight of 600 newtons if they both really come to the same thing? To find the answer to that, let's go to the moon. It doesn't feel as if you weigh so much here, does it? Let's see how many newtons are pulling you down on the moon. Only 100. Why is that? Because the moon is much smaller than the Earth, and therefore has much less mass. So its force of gravity is also much smaller, only 1/6 that of the Earth, in fact. This is why your weight on the moon is only 1/6 of your weight on Earth. What about your mass? On Earth, it was 60 kilograms. How much will it be on the moon? 60 kilograms. Exactly the same, of course. You don't get any smaller by going to the moon. You don't change. Only the force of gravity, and therefore your weight changes. That's the big difference between mass and weight. Wherever you go in the universe, your mass stays the same. Only your weight changes. So if you're not as slim as you'd like to be, don't eat so much. You should join the Mass Watchers Club, because you've got a mass problem. But if all you want to do is lose weight, go to the moon.
My weight didn't really change here. Or here. My mass of 55 kilograms always means a force of gravity of 550 newtons. To find somewhere where my weight really does change, I'm going to have to travel a little bit further. My first stop on this long journey is the planet Jupiter, an enormous gassy planet. I couldn't really land on Jupiter, but imagine I could. Now, here on Jupiter, my mass is just the same as back on Earth, 55 kilograms. In space, on Earth, on Jupiter, there's still the same amount of stuff in me. So why do I feel so heavy? Jupiter is much bigger and heavier than Earth. It has a force of gravity too, but the force of gravity is much stronger than on Earth. On Jupiter, my weight is no longer 550 newtons. It's nearly 1,400 newtons. Wow, that's heavy. The force of gravity on Jupiter is 2.5 times gravity on Earth. Even picking up these bathroom scales is difficult. And bouncing on my pogo stick is almost impossible. That is until I switch on my turbocharged boosters. See you later. I've got a long journey ahead. Nearly made it to the most recent planet to be discovered and furthest away from Earth, Pluto. Pluto's even smaller than our moon. My mass is still the same, 55 kilograms. But my weight is only 20 newtons. I weigh the same as a couple of boxes of cornflakes weigh back on Earth. On Pluto, the force of gravity is much, much weaker than on Earth. Easy, does it? I don't need my turbocharged pogo boosters. Here. I'm not sure where I am now. Far beyond our solar system, in the middle of outer space. And you know what? At last, I've done it. I am totally weightless. There's no force of gravity from any planets because they're all so far away.
My name is Nicole Stott, and I'm a flight engineer with Expedition 20 on the International Space Station. And we're here today with you on the International Space Station and the Japanese Laboratory Module.
Hi, I'm Bob Thirsk. I'm also a flight engineer aboard Expedition 20. The topic for today is weight versus mass, a heavy-duty concept.
So what is weight? Weight is the vertical force exerted by a mass as a result of gravity. Weight also means the strength of the gravitational pull on the object. That is, how heavy is it? Weight is dependent on gravity.
On Earth, in a 1G environment, an astronaut in his spacesuit would weigh 360 pounds. On the Moon, in 1/6 Earth's gravity, the astronaut would weigh 60 pounds. In orbit, he would weigh 0 pounds because weight is dependent on gravity and the effect of Earth's gravity is not observed.
Orbit are said to be weightless. The object's mass is the same, but their weight would register 0 on a scale. Weight varies depending on if you're on Earth, the Moon, or in orbit. but your mass always stays the same. The first thing that Koichi and I would like to do is demonstrate that we're actually on board the International Space Station and we're in a weightless environment. So let us show you a few little tricks here that'll make that point. I'd like to have an arm wrestle with Koichi. Let's see what happens.
This is great, actually. Okay. Then small.
One of my favorite Japanese sports is sumo wrestling. We're going to try to sumo wrestle.
That is super.
The somersault.
Okay, Nicole, show us your stuff. Where'd she go?
Oh no!
Come back. It's Superwoman.